Hello everyone, this is meteorological instrumentation and we are about to start talking about measurements and instruments. And the first instrument that we're going to talk about, or the first types of instruments, is barometers. Barometry is the method by which we measure pressure in the atmosphere. We're going to start out talking about the history of the barometer and then also pressure units after that. We're going to get into the different types of sensors, and then we are going to talk about bringing our station pressure down to sea level and the method that is employed to do that. And then finally, we are going to talk about the errors in making pressure measurements. So first, let's look at the history before we get into theory and pressure units. The first person to build a barometer was Evangelista Torricelli, and he did that back in the 17th century. He met Galileo 3 months before he died when he was imprisoned at his villa. He read all of Galileo's works. He thought he was a great scientist, and he talked with Galileo about a lot of different things, but he created or invented the first barometer trying to solve a problem that engineers had at that time. They realized that you can only have water pumped up to approximately 30 feet. Above that, there was a problem trying to get water up that high. And he thought he'd recreate the problem with mercury, or actually at that time it was called quicksilver, because it had a higher density than water, so he wouldn't have to create such a big device. It could be smaller. So what he did was he filled a column, or had a tube filled with mercury, turned it upside down, and that left a little space at the top of the column, or the beaker. And he theorized or postulated that that area didn't have any air or anything in it, and that's when he discovered, or when he theorized, that that was probably a vacuum. It fell to another scientist later on named Pascal to actually prove that that was a vacuum. And then also he had some ideas or concepts about wind. Specifically, he thought that wind was a result of air density differences across the Earth, and that was caused by temperature differences. Barometer, the word comes from the two Greek words baros, which means weight, and then metron, which means measure. So what the barometer does is it measures the weight of the atmosphere. You can compare that, and its equivalent weight is measured in mercury. The theory, a little bit of theory about the gases in our atmosphere, and then also the pressure that they impose. Pressure, by definition, you guys probably learned this back in 110, pressure is the force over a given area. And force could be anything. We're talking about gases, so this is the force that's supplied by gases in our atmosphere. If you look at it on a molecular level, really what's happening is molecules are zipping around in our atmosphere, and they're imparting with different surfaces. And they impart with, or they strike everything, and that momentum is transferred to that object. So you can think of it as the momentum or the force that's imparted by molecules bouncing off of surfaces everywhere. Divide that by the area that they're bouncing off of, and that will give you your pressure. There were some scientists that lived back in the 17th and also the early 19th centuries that came up with some concepts about pressure. One of them was Robert Boyle. Robert Boyle and his assistant Hooke lived in England back in the 1660s, and Robert Boyle did an experiment where he had a pressure, or actually had mercury, or a mercury barometer hooked up to a sample of gas. And this was a basic manometer. We'll talk about manometers later on. but he varied the volume of the gas. Varied the volume, and as a result, he found that the column of mercury went up and down. In other words, the pressure changed. Now, this was for a given room temperature. So, this concept was called Boyle's Law. And here's what Boyle's Law looks like. It says that pressure is inversely proportional to volume, or the product of pressure and volume is a constant. So what that means is that if pressure goes up, volume will decrease for a sample of gas, for a given amount of gas, and conversely, if pressure goes down, volume will go up. The next concept or theory behind pressure came from two individuals. One is Charles and the other one is Gay-Lussac. They lived at the end of the 18th century or beginning of the 19th century. Ballooning was all the rage, hot air balloons back then in France, and both of these gentlemen lived in France. They were trying to design a better balloon, and they came up with this concept, which we know now as either Charles's Law or Gay-Lussac's Law. And their concept or their idea was that the pressure is directly proportional to temperature for a given amount of gas if its volume is constant. So this is what it looks like here. This is your empirical relationship, the Gay-Lussac law, showing you that if pressure increased, so did temperature, or vice versa. If pressure decreased, so did temperature. So that was at the beginning of the 19th century. And there's two relationships now, one with pressure and temperature, another one with pressure and volume, Boyle's Law. And then if we put those two together, we'll get a third law, which is your ideal gas law. This was discovered by Clapeyron at the beginning of the 19th century. Clapeyron was a French engineer and also was working on steam engines. So they're trying to come up with some concepts as far as how steam engines worked. So the ideal gas law, PV is equal to nRT, shows that there's a relationship between these three variables: pressure, volume, and temperature. Now, the ideal gas law can be used for one gas, one individual gas, if you're looking at one gas, or it can be used for a mixture of gases. So the constant there, R star or R, represents the gas that you're going to use. If you use it with moles N, then you use the universal gas constant, but you can come up with a gas constant specifically for individual gases, and that's what you see in the second equation, that R. Let's talk a little bit about pressure units now. And the SI unit of pressure is the Pascal, and that was brought about by an international convention in 1971, where they decided to give Pascal credit, not credit, but give him a unit for all the science that he did in the past, named after Blaise Pascal. And here's the most basic SI units, how we come up with pascals for pressure. If you think of pressure as a force per unit area and force is a mass times acceleration, then pressure is a mass times acceleration divided by area. It's a force per unit area. So if we put in our SI units for mass, for acceleration, and for area, it would be, let's see, mass is kilograms, acceleration is meters per second squared, and area is meters squared. So after canceling out the duplicate variables, or not variables, but units, a Pascal ends up being a kilogram per meter per second squared. There are lots of other units that are used for pressure. Here in the United States, we've been using millibars for a long time. However, since pascals are the SI unit now, the correct unit, meteorologists like to use hectopascals, which is 100 pascals, because 1 millibar is approximately 100 pascals. Other units of pressure that are common, inches of mercury are used all the time in aviation when we're talking about altimeter setting. In other applications in engineering, they use pounds per square inch. In chemistry, they use atmospheres quite a bit. And here are the conversions between each type of pressure unit. There's a few other conversions. As I mentioned, 1 hectopascal is equal to 100 pascals. And then 100 pascals is equal to 1 millibar. That's something that's very common or very familiar. That's all I have for you for this lecture. There's a second one that I've created, and that will be on the different types of pressure. So make sure you listen to that video.